exploring complex networks, matrix-based and multiscale approaches for pattern recognition. And to give you a brief explanation to show you the outline of this presentation, first, I'm going to start with the motivation, followed by the goals of this PhD, a little bit of the background. And here, because we have a limited time, I'm going to present you 3 of the works that we developed in this PhD, the conclusions and contributions, and throughout the whole presentation, I'm going to mention briefly about the healthcare modeling that was also part of this work. So, of course, starting with the motivation, for centuries, researchers have been using a reductionist approach in order to analyze a system in the universe. So, for instance, we tend to observe an object in a system as a single and isolated point. However, this is not natural for many real phenomena. So we know that in reality, we know that the surroundings of the object does affect this object, and also the dynamics is really important for us to understand the system. So in this sense, complex networks comes as a natural tool for modeling data, and we can use the advantages of going from this reductionist approach to a more integrative one, and then use this model to understand systems and to explore the systems. And of course, because we know that we have many advantages here using the complex networks as a natural tool for real systems modeling, we can apply the model in many domains. So here we can go from sociology to epidemiology, and we also apply these models to benefit many data science tasks, both in the industry and also for science. And of course, in our academic journey, I believe that one of the major inspiration for having new ideas in a PhD project is our own path. So since my undergrad degree, I have been working with computer vision techniques, and my master degree, for instance, was focused on texture classification. And also because I'm part of the scientific computing group that is supervised by Professor Bruno, we are a data science group that has many works that combines these 2 techniques. So the advantages of complex networks and computer vision. So we have many works that I'm going to show you later that combines the advantages of complex networks modeling to classify images. So I believe that this is one of the major motivations for this work. And the goal of this PhD is actually to propose new methodologies in order to increase the classification accuracy of complex networks. And in order to do that, as I told you before, in the motivation part of this presentation, we are going to combine computer vision techniques and graph theory. And of course, because this PhD we've been through the COVID pandemic, and I have a project in rare diseases, we also has a secondary goal to combine the advantages of graph theory to model healthcare data. So these are the 2 main goals of this PhD. And here I can show you the diagram of this PhD journey, where you can see the main projects that we have done. So in this presentation, I'm going to focus mainly on the classification of complex networks, especially focused on the matrix-based algorithms and the multiscale approaches. So these 3 methodologies here. And we have the other papers focused on shape classification, and also the COVID-19 seer-based model, and a work for rare disease codification. So we have these two different approaches. So the primary goal of this PhD is complex networks classification, but we also have another branch that is healthcare modeling. And now that I explained you the main goal of this PhD, let's start with some of the definitions. So a graph consists of a set of nodes connected to a set of edges. And usually we tend to think about the graph as nodes being circles, and they are connected by other nodes, and the links are represented by lines. And when we talk about links, we have domain-dependent approach, because the links can be physical links, such as in metabolic networks, or social links, so in friendships. So we can model different types of systems. And going back in the history of graph theory, we have that in 1736, the history of Königsberg and the 7 bridges, and I really like this story, because the mathematician Karl sent a letter, not a message, to Euler, and he was asking Euler if it was possible to cross the 7 bridges of Königsberg without repeating any bridge. And after many exchanges of letters, Euler noticed that there was no such geometry capable of represent this type of system. And then he proposed the geometry of position that later we know as the beginning of the graph theory. And as another side story, we know that 2 bridges of the Königsberg was destroyed in the Second World War. 2 were destroyed to construct a highway, and 3 of them remain in Russia. And from that, especially in the 60s, we have the proposal and the studies of many synthetic models that we know in forehand, the main characteristics, the main degree distributions, for instance. And we can see here the proposal of random networks, small world networks, scale-free networks. And of course, because we talked about the advantages of using this type of models in real data, we have studies in both industry and in science, in the research field, of social networks, community diseases, metabolic networks, and also because we have been through a pandemic in the recent years, we know that the studies of complex networks are also really important for us to understand the dynamics of communicable diseases, such as the COVID-19. And of course, with more data, we can go to infinity and beyond with more ideas that can be applied in science and the industry. And because here we are doing a PhD, we have to narrow our study to be more specialist. So here I'm showing you some of the background studies that were an inspiration for this PhD. And because I told you that many works in the scientific computing group already combines these 2 techniques, the computer vision and the complex networks, for classifying the images, here are some works that models the image as a complex networks and then use the features from the complex networks for classifying the image. So here we have shape analysis, texture analysis, and we have some works on this area. However, here, as I told you before, the goal is not to classify images, but to classify complex networks. So I have to mention here an important work published in scientific reports, and the work from Miranda et al. Is focused on create cellular automata from the complex networks, and the cellular automata evolves according to lifelike rules, and the features from these cellular automata based on the complex networks are used to classify the complex networks. So this is the goal of this paper is similar to what we are looking for, so to classify complex networks. And also because the work of the previous work had great results, we have here two other works that also uses this idea of cellular automata and to understand the features over the evolution of the cellular automata and classify networks. So we are going to use them as a benchmark for our comparative results. This is why I'm showing you these specific methods. And also we are going to compare the results of our approaches with the classical metrics from the complex networks. Okay, so now we can go to our first proposal, exploring ordered patterns in the agency matrix for improving machine learning on complex networks. This work is published in Physica A, so you can go later and find more details. And if I tell you, imagine a complex network, a graph. So I bet you're thinking of these dynamics of circles and lines, right? However, there is a different representation that we can go back and forward, and we can retrieve the same average degree, the same diameter, the same clustering, the same betweenness between both of the representations. So here on the right side of this page, I'm showing you the agency matrix of the graph on the left side. So the agency matrix is built in such a way that if two nodes are connected, for instance, 1 and 2, the value of the position relating these two nodes is 1. In here, we have white blocks. And if they're not connected, for instance, 2 and 4, the value in this position is 0, which means here we are representing this image as black blocks. Okay, so, and when I think about a new idea, one question that comes to my mind is that, have we exhausted all the simplest analysis on complex networks? And because we already use agency matrix in many studies over complex networks, and also because sometimes it's easier to use the matrix representation of the graph to calculate some metrics. For instance, we come to another question: can we keep exploring agency matrix in order to classify the whole network? And here it's important to emphasize that we are not trying to find features and to classify and to label a single node in the graph. We are trying to classify the whole network. We are trying to find a label to the network, to the graph, okay? So it's important to emphasize that, because we know that there are different types of studies in this field of complex networks. And because we have a strong background in computer vision, and when I look to this agency matrix, I tend to think about distribution of pixels and then also texture. So the idea of combining complex networks and computer vision. So in order to explore and try to label the graph, then I can explore and try to label the image of the graph. Here I'm using the agency matrix. However, although it seems like a good idea, here we have a problem. So if there is no a single representation of the order of the nodes in the agency matrix. So if I somehow construct the agency matrix in here the numbers are just for an example, but we don't have numbers in the different models, especially in reality. So here, if we draw the agency matrix in a different way, we can go back and draw the same graph with the same connectivity, with the same connections, but the image is different. Which means that, imagine that we're going to make a machine learning algorithm, and we need to enhance and highlight the patterns on the graph. And for instance, you take an example from a different source, and the same model, the same label, now has a different degree, pixel distribution, in the sense because we are reading the data from a different source or from a different period of time. So we don't know for sure, we cannot guarantee that for a single graph, we're going to have the same representation, the same matricial representation. And so the first step of this work is actually to propose a methodology for agency matrix based signature for complex networks. And this idea is actually to seek for a unique representation of this pixel distribution for a label in the data set. And of course, because we know that the centrality of the nodes are, for instance, the degree is simple yet a powerful metric of the node, the first idea is actually to use the degree of the node as to sort the nodes in the agency matrix. It means that the node with the highest centrality, the highest degree here, is located in the highest row and column of the agency matrix. And of course, because we know that in a graph, we have several nodes with the same degree, we use the betweenness, the clustering, the closeness, and the eigenvector in this order as tiebreakers to choose which one of the nodes are going to be located in the first positions. So, okay, this is how we're going to try to seek for a sorting method in the matrix, because here we need to find and highlight the patterns for the computer vision techniques. And as a first result, we decided to visualize the networks and see whether there is a difference when we can highlight the patterns in different models doing this ordination process. So here we have the first result. It's a visualization of the proposed ordination. So here for Barabasi Albert, we can see that the hubs are located on the top left corner of the image. So here we can see that because we really understand how the sorting method works, we can understand how the metrics are drawn in these images. And so here in the Barabasi Albert model, we have the presence of hubs here. And because the majority of nodes have lower degree, we can see that when we go down, we have a lack of edges. For the random networks, we see that the ordination tends to be random. So we see how the model is built is presented here in the image. And for geographical model, where we have the distance to connect to nodes, here we can see the presence of some veins in the sorted image. And for small word networks, the Watts-Strogatz model, we see here the presence of a diamond shape that can represent the shortest paths among the nodes and the high clustering coefficient. So this is the idea that we have looking at these four models, and we can see that the application of the sorting proposal indeed highlights the most important features from the synthetic models. And of course, because we have to go inside the data set to see if this is true for the whole data set, we can check even with if we have different average degrees, the patterns remain in the image. So here, 3 examples of Barabasi-Albert with the same number of vertices. Here, random networks. For the small word networks, we can see the veins, that the veins remains in the images. And for geographical networks, we can see here also the presence of veins, although we have wild distribution of edges here. And of course, because I told you that our primary goal is actually to try to find a way and develop new methodologies for the classification of complex networks, now we move from the visual inspection of these images that, okay, this was a clue that this work might work for computer vision techniques. And now we want to classify the images based on computer vision techniques. So here we tested the methodology in 12 different data sets. 5 of them are synthetic models and 7 of them are real networks. And for the computer vision approach, for the computer vision step of this exploration of the agency matrix, I'm using projection that it's actually flat the image in one axis. So we somehow are evaluating the degree in a different order. The VGG19 CNN model. So here I'm not using the VGG19 for classification, but actually I'm using the last but one layer, and I retrieve the features from this last but one layer and use that as input for SVM. So also I'm using traditional texture classification methods such as CLBP, and also I'm using the 7 moments of hue for trying to understand these images. And I'm using as well cross-validation with k equals 10. And because another question that came to my mind is that, okay, does it make a difference in sorting these matrices? What's the difference between I'm trying to explore the pixel distributions in the regional way? I read the data set and okay, I'm going to apply the computer vision techniques. And what if I sort the matrices? So, well, you can see here that our first quantitative results show that we indeed have a difference in the classification of the complex networks when we apply this sorting methodology. So, for instance, for Kingdom data set, we have the result of 100% when we apply the sorting methodology, and 99.6 when we use VGG19. And for instance, for Basilis here, we also achieve 99.9, whether before for the unsorted matrices, VGG was able to classify the model with 94.56%. And also here, we were able to decrease the standard deviation. And for noise, we were able to classify scale-free noise with 10% of addition of noise in the synthetic models with 100%, and noise equals to 20% with 100% in this methodology using VGG19. And it's important here that the best results with this approach is regarding VGG19, and in this case for the binary images, we also have the good results with projection. So the sorting method does make a difference when we are trying to explore the agency matrix. And of course, because we have to compare our results with the state-of-art results in complex networks classification, here I'm comparing the results of the approach with the results from LLNA methods that I previously showed you in the background, and also with structural measures. So here for the classical measures of complex networks, which is a concatenation of several features from several metrics from the networks, here we can see that we are able to classify the synthetic models with 100%. So our focus is actually to classify the synthetic models with good result, but also the real networks. For instance, here you can see that the classical metrics classify the Fundi data set with 54.90%, while we have the best result among all the techniques that we are comparing of 88.33%. So it's a great result regarding our approach. And also for this last data set, we also have a great result compared to the previous one, and we are able to classify actinobacteria with 99% of accuracy. And if we go further on the classification of the data sets, we can see that although we can classify all the 500 scale-free graphs of the scale-free data set with 100%, in the synthetic model, we indeed see here the difficulty in classifying 16 graphs, and there is a confusion between the geographical and random networks. So this is understandable because we saw previously how the shape of the sorted agency matrix are for both methods. So okay, we understand that we might have room to improve and to highlight that model. However, the overall results are really good for this data set. So we have the area under curve of 0.99%. So, okay, now I presented you the first proposal of this PhD. And this is a way of changing the perspective in looking at the complex networks and extract classical metrics from the complex networks. And here we are doing the opposite of the works that I showed you before. So here we are modeling the complex networks as an image, and the images can go back to the graph. So we have this linear representation. However, we have to do the sorting approach to highlight the patterns. And this approach can be used both for visualization and for classification. And one of the things that I like the most about this approach is the low parameterization. If you read the works from LLNA, you can see that the time consuming for parameter setup is huge. So here we don't have this parameterization setup. We can go straight from the analyzing the centralities of the images. and we do have good results compared to the literature. So we even have better results. Actually, 8 out of 12 data sets there have outcome the results of the previous state of art. So this was one of our first ideas for this PhD, and we saw that we could go on and work in the idea of applying computer vision techniques for classifying complex networks. So Professor Ademir came to me, and he was thinking that we could then improve this methodology and add some more information on the matrix-based approach. So the idea is, okay, we are working with binary images in that proposal. However, how can we create meaningful matrices with colors, or at least we can move from a binary perspective to a perspective that we don't have only zeros and ones. So because our complex networks have no weights, the edges have no weights, and then we have to find a way to create a matrix where we seek for features that combines two nodes, because this is how we can build the 2D representation of the graph. So the result of these ideas is explained in the second proposal: enhancing information ordered patterns for complex networks classification. Again, the focus is on the primary goal of this PhD, through exploration of vertex similarity. And here you have a clue of how we're going to seek for this. We're going to go on with this approach. So the idea here is that we use the Jacquard index for creating the new matrix from the graph. And here we don't have in 101 methodology, but we see that the Jacquard matrix is created following this equation. So for two nodes I and j, the Jacquard index is actually the intersection between the neighbors of these two nodes divided by the union set of these neighbors. Actually, the size of these two sets. So it's important to emphasize that this work of Jacquard index is used in complex networks, usually for link prediction. And here we are not computing the Jacquard index for nodes that are already connected. And here I have an example. So for instance, I have this image here on the left side of the page. And here is the Jacquard matrix that I built from computing the Jacquard index for each pair in the network. And as an example, for you to understand the index, for instance, if I have nodes 1 and 6, they share node 7. They have one neighbor that they share. So the first we use 1, and then in total they have 5 neighbors. So 1 plus 1 divided by 5 is 2. So here in the image we have 1 divided by 5 equals 0.2. So in this sense we construct a Jacquard matrix. And here, because I'm also trying to highlight the patterns, I'm using the sorting metrics for each node, each node. And so here you can see how we used in the previous methodology as well. We compute the degree, the betweenness, the clustering coefficient, and the closeness. And we only use the following metrics if we have the similar degree or the similar betweenness and so on. So here is we go from this initial Jacquard matrix to this sorted Jacquard matrix. And we use the same idea of centrality sorting to move from the first matrix to the last one. And again, we go first with the visual inspection of this proposal. And here I have to say that, as you saw before, we have values for this index from 0 to 1. But here I'm using the color map jet just to improve the visualization. And you can see that the patterns in the scale-free models, they show that for the top left of the matrix, you can see that we have low Jacquard index, or because we have a lot of connections, so we do not computate these points. And here we can see that we have a similar pattern when we compare the sorted agency matrix and here the Jacquard matrix, because we know how we sorted the nodes even here when we are computing the vertex similarity. So here you can see that the nodes with lowest degrees have highest similarity between their connections. And although we have here a proposal of a random network, it's interesting to see that we can see somehow a pattern in the randomness. So here we have the random model with a rainbow shape in the colors and in the vertex similarity. So going from the blue, so the lowest, to the highest, and going back to the lack of similarities here. Okay, so this was something that was really integrating in this approach. And actually the random model seems like to be the geographical one. So here we have a noisy image here from the methodology applied to the geographical models. And for the case of small world networks, we have an homogeneous image. So here we see that we have either high connectivity, so we don't compute the Jacquard index, that this is why the majority is black, or we have, because we have high clustering coefficient and the nodes tend to be connected and we have shorting paths between the nodes, we have here a flat and homogeneous pattern for the Watts-Strogatz image. Okay, and if you go further again inside the data set, we can see that the patterns remains even though we get different examples of the same model. So this is what we are trying to do. We are trying to classify the image based on the model, and it seems like it's good for classification, right? So again, the results in the visualization aspect is really good. And because, again, we are looking here for a quantitative result regarding the classification of complex networks, we are using the images that were outputted from the Jacquard sorted based matrix. And here we are using the same 12 data sets, the same computer vision techniques that we applied before. And now we can go straight to the results. And for the first data sets here, we have that our approach was able to classify the synthetic synthetic data sets with 100% of accuracy. And also we have a good results for actinobacteria, again, reaching 99.5%, which is really good compared to the state-of-art results in the literature. So we can go from the top of 95% to 99%. So we indeed achieved our goal to increase the classification in the complex networks. And for bacillus, for instance, we do not overcome the result from the previous approach, but we have good results compared to the literature. And for Kindle data set as well, we have a great result. So it means that the idea of creating these colorful images, this image with more information, so going from the binary first proposal to a matrix that uses the vertex similarity to compose the image that we're going to use in the classification task, we do have good results. We do achieve our primary goal of increasing the classification rate in complex networks classification. Again, we are changing the perspective. We are looking at the graphs from the image side, and we can use this approach for visualization and for classification. And because I told you that I really like to think about simple ideas, this approach has also a low parameterization. So we don't have any parameterization here. We use the Jacquard index to build the matrix, and we go straight to the use of computer vision techniques. So the methodology here is more related to build and highlight these patterns, so we can combine them with the application of several computer vision techniques. So here we can explode in ideas and combine with different CNNs, different texture analysis algorithms, and the results are good. And finally, here we go to our third approach, which now we move from the matrix-based approach to the multiscale approach of analyzing the complex networks. And as a side story, I want to say that I was traveling overseas, and because I worked with distance transform during my master's degree, I was thinking in a way of how could I bring this idea of analyzing different scales in the image that I used before and apply this in complex networks. So I was traveling overseas and I was thinking about new ideas. I looked at the ocean, I saw the circular waves in the ocean, and I was like, okay, I think I'm going to work with multiscale approaches again in the PhD. And the idea of multiscale appears also in the distance transform network for shape analysis that it's published in Information Science, that we use the idea of distance transform for classifying, and then we model the distance transform as a complex networks, and then we use that for classifying the image. Here we are classifying images from the aspect of complex networks modeling. And also, of course, it's totally a different idea, but the idea of multiplex also appears here in this paper that it's a seer-based model that includes the demographics of Brazil to construct different social layers. And then we have this idea of building layers again. And how can we use that idea of multiscale approaches to classify the images? So looking at this image, I want to break and to explore the graph in different aspects in order to try to explore different granularities in the graph. So the idea came in because we have this K-core methodology in graph theory. So the K-core works as follows. For each K-core that we want to compute, we have to remove a vertex with a degree less than k and their edges, and we repeat this step until we do not have any nodes with degree lower than the k. So the k car here, we have a parameter, so the k, and here you can see that for k equals 1, we have the whole networks, and if we have an isolated point, the k core removes these points. And for k equals 2, we have to remove the blue vertices. So we go further, and for each one of the cores, we have different connectivity, we have different average degree, we have different statistical metrics from the graph. So the idea is to, from the k core, we do this decomposition, and then we are able to explore each graph, each subgraph as a single graph, and then we can retrieve features from these subgraphs and combine them to work as a final vector, as a combination of these three, in this case, these three cores. So the idea here is to explore the granularities of the network. And of course, because we have the first proposal, here we have the option of exploring the subgraphs, the k cores, with the traditional aspect of complex networks analysis, or we can use the idea of matrix-based approaches that I presented before to extract features and explore the images of each core. So we have two possibilities here. And because here are introduct the parameter k, I have to propose a methodology to find this k core. So here we are using k equals 1 to a maximum k core, and we are using the overall degree of a subset of 10% actually of the whole data set to evaluate the average overall degree, and we are using this average degree as the maximum k core. So then we can build a matrix of features, and we know that we have we can concatenate it with agreement of this is the first core, this is the second core, and so on. So here we can see that the idea of exploring the images, here I'm showing the image because it's easier for visualization, but here you can see that when we increase the k value, we remove the nodes with lowest degrees, and it's like we are zooming the image. So we are exploring different things. And also here in the scale-free models, we have the example of for core for each one of these different models, and we can see that indeed we are able to distinguish the patterns and to classify, hopefully classify the images based on the k-core decomposition. And again, for the classification part of this work, here we have the addition of exploring the classical metrics from each one of the cores, and then to combine the features from each core into a single feature vector. And also we are going to explore as well the ideas of combining computer vision and complex networks. And here we are exploring 7 data sets. So finally, the results of this third proposal. Here I have the results of the classical k-core, which means we're exploring the network as it is. So the composition, and then to a combination of features from each one of these this K-core. And for scale free, we have a result of 100% of accuracy. And for Kingdom, we have 98%, which is really good compared to the previous approaches based on cellular automata. And for Plant, we have the best result over all the previous methodologies. And for actinobacteria, we also have a good result compared to the previous methodologies. And here you can see that we can use both the K-core applied to the K-core idea applied to classical complex networks methodologies, and also using the idea of the agency matrix based approach, or then we can go further and use the similarity of nodes. And finally, the conclusion of this third proposal is that we can use graph decomposition to increase the way that we explore the complex networks for classification. In this case, we have two possibilities. We can explore the graph, so to the classical structural measures from the graph, or we can use the image approach. And here we can see that we can use the proposed for visualization and classification. Here I added one parameter, which is K. However, the K, the way we propose it to set up this K value is simple and it's fast. So we use a percentage of the set, we just calculate the average degree, and we use that as maximum K for the K-core algorithm. Again, we have good results compared to the literature, so showing that the three approaches that I presented is great. They are great for classifying the complex networks data sets that we are evaluating here. And finally, the conclusions of this presentation is that we have proposed new methodologies for characterizing complex networks using both two-dimensional matrix, so using the binary and the vertex similarity based approach. And also we are using the multiscale representation when we use the K-core decomposition. We have competitive results, especially for real data sets, because we know that the synthetic models are able to be classified with classical metrics, but for real data sets, this is the challenge that we want to overcome to have better results. And this is important those are important methods because they are suitable for several applications. So we can have, if you have a data set of different labels of networks, we can use this methodology in order to label the graphs. And of course, here, one of the things that I like the most about these three works that I presented today is the low parameterization. So here we have only one parameter that we have to set up, which is the K of the K-core. And all the approaches, they gave us the possibility to explore more and more the computer vision techniques. So we can use different, for instance, convolutional neural networks to explore the complex networks. And we know that recently, in the past years, the area of image classification developed new methodologies, so we can combine the advantages of this research area and then of the complex networks modeling, because in the end, we are exploring the connectivities of the system. And because we have a limited time here to present the whole project, here I'm showing you again the diagram of this PhD. So if you have further questions regarding any of these works, I am glad to answer. And also, I would like to thank again for the professors to for accepting my invitation to participate in this such important moment in my academic life. I'm really glad that I was able to be here today with you. And also I'd like to thank Professor Odemir, because I'm really grateful to have you in my journey. Thank you. And I'm open to questions.